Okay. Hello, hello, hello. Okay, hopefully this is on live. Alright, so this is Junichiro Horikawa. This is a live stream for Houdini tutorial live stream called as Houdini Algorithmic Live. This is 125th episode, and the topic for today is to create a rather quick, low-cost, quick SOP-based fluid simulations, like you're seeing right now. Now, this is not really based on any physical simulations like Navier-Stokes or such a high-cost simulations, but it's more based on just a simple vector calculations. So if you're looking for a physics-based accurate simulations, then this is not the one you're looking for. But if you're looking for a rather low-cost, quick, easy to implement fluid system, then this might be the one you could use. So the result will be something like this. You have a basic, you have some guide curve to make the overall flow of the fluid. And you also have some obstacle like a rock to change some directions of those fluid. And you can just change it parametrically like that. And you can get the result quite quickly. So yeah, might be useful in some case. As always, but just to mention, this is not really production ready or anything, so just enjoy it as some experiments. Okay, so this is what I'm gonna do today. So let's do this from scratch. Okay, so the things that I need is a base plane to create the fluid sim, also a base curve which you can use to direct the fluid, and also some obstacle object. Okay. Hello everybody, thanks for joining. Okay, I have some comments here. Do you think focusing on water FX as a beginner is a good decision? Think so. I mean, if you are looking for a DOPS, like physics-based simulations, then I'm not the one to teach because I don't really know DOPS much. But if you're looking for some low-cost VEX-based kind of a fake sim, then yeah, maybe I can show you some. So let's do this. I am going to start by creating some grid as a basic base for the simulations. Could be any size. I can just choose by yourself. And I'm going to make the rows and columns 2 by 2 so that I don't have any grids on it or edges on it inside. Now I'm also going to create some curve which is going to be used as the base flow to direct the fluid. You can have multiple number of curves, so let's try to create multiple curves. Okay, I am going to use poly curve, or it was not called poly curve. okay, curve polygon, and just plot random points. Press enter. I'm also going to create another curve so that I can test with a multiple number of curves. Now this is currently a poly curve, so I'm gonna smooth this out to make it more like a nerves curve. So let's do that by, I'm going to use a resample so that I can add multiple number of points to these curve, as well as smoothen out by changing the tree polygon as to subdivisions or interpolating curve. Maybe subdivision is fine. Okay, and let's try to change the curve a little bit more so that the direction of the first one and second curve will be a bit more different, a bit more dynamic. Okay, let me change this to a mouse. Try to change the direction a bit more dynamic so that we can see the changes to the flow. Maybe something like that. Okay. Okay. So starting from the starting point of this curve to the end point, this is going to be the direction, the basic direction of the fluid. So you have, if you have two curves, then the final vector field is going to be affected by the distance to this original curve, and try to consider how much it affected by those two curves based on the distance on each point on the space grid. Okay, so things that I'm gonna do is to use create a vector field. I can either use volume or based on the points on the grid, but in this case I'm going to use a volume to create the vector field, since it could be used probably later for, I don't know, 3D geometry as well, if you want to create not just on the surface, but if you want to create a fluid inside 3D geometry, then using volume makes sense. Okay. Then let's create a volume. I'm gonna connect the volume to the grid so that I can create a flat volume shape. Now I'm going to make it as vector because I want to make a vector field. Then let's name this velocity. The name could be anything. And just to visualize how it looks like, I'm just gonna make the x-axis equal to 1. Okay, so it looks flat, it's fine. Now let's also determine the resolutions of this volume. You can do that by, you can set the resolutions for the volume here. Now, higher resolution you have, higher more dense vector fields you could make. So let's make it 50. And if you have larger area and if you want to create more complex vector field, then you might want to increase this later, but let's stop by 50 for now. Okay. And let's check the volume shape. So it's 50 by 1 by 50 for all XYZ direction. Okay, now it's time you could start creating a vector field. Modify the vector direction to this volume using this basic curve as the base direction. Okay. I'm gonna do that by using volume wrangle. Okay, so here is where I'm going to modify the vector field somehow using vector-based uh, calculations. So how would I do that? Let's think. So I have a base vector field and each point I have to determine which direction I should point that to, point these voxel to, and I currently have a base curve as a direction going from the starting point to the end point, to the starting point to the end point. Now at each point you want to calculate how much this point be affected by the first curve and the second curve. Okay, and you're gonna determine the effect ratio by calculating the distance. Let's say this is d2 and this is d1. So you calculate the minimum distance between two curves, and based on this distance, you're gonna use this as a weight, the weight value, and how much this point is gonna be affected by these direction. So more further the distance is, you get less weight. So closer the distances, you have more weight to be more affected by this curve. So since this point is closer to the number 2, the curve number 2, you have more effect. You have more weight from this curve, and since the distance to this first curve is further, so you have less weight for this direction if you're gonna pick up the distance where it's being projected on this curve. So in this case, you are picking this direction, the tangent vector value, right? And you're gonna bring that here, multiplying by the weight 2 and weight 1, and in the end the final direction you get is something like this. Okay, so you do this for all the points on a volume to estimate the vector value. Right, so that's the basic idea here. So let's do that. So first thing first, for each point, for volume, for each voxels on volume, you want to calculate the distance to each of the curve coming from the second input. So I am going to create a loop with a number of primitives coming from second input, and primitives okay, then let's first calculate the minimum distance to each of the curve. So the current point position of the voxel can be retrieved using @p volume wrangle. So and in order to calculate the minimum distance, you can use a function called xyz distance, and you're looking at the second input, and by specifying the group filter by using a primitive number itself as a string, you could specify which curve you want to project the point to. Then as a result, you get the distance, and also if you want to get the tangent vector value, you might want to also output the primitive and UV, which can be retrieved from this XYZ distance. So these are the output parameters. This is the input, this is the input, and as an output you can get the minimum distance, and this distance can be converted into a weight value, and you could also get a tangent vector value by using prim UV from the second input. And currently we don't have a tangent vector value assigned to these curves, so let's also make that. If you go to the resample node, you can turn on this tangent attribute, which will create a tangent vector for each point on a curve. If you look at the geometry spreadsheet, on a point attribute, there's tangent u value, which is this direction along the curve on each point. So this is why you want to get on this volume wrangle, and somehow the code is gone. Okay, gotta rewrite it. So where was I? Looping all the primitives. And I was having a primitive number as an output, UV as an output, calculating the minimum distance using XYZ distance from the second input, looking at specific curve number, primitive number, using at P as a start projecting point, and get the output primitive and UV. Then you could get the tangent u vector value by using prim UV second input, and get the tangent u attribute from prim UV. Okay, save it. Okay, so hopefully now you should be able to get the distance, minimum distance from each of the voxel point to the curve, the closest distance, and also the projected point tangent vector value. So having those two values, you can calculate the weight and how much the weight must be multiplied to this tangent vector to be used as a final direction on each voxel. So the final direction, I am going to make it outside the loop, starting with 0, 0, 0. Then inside the loop, I'm going to update this direction by adding the tangent tangent u multiplied by some weight value. Now you also have to calculate the weight. Now the weight has to be bigger when the distance is smaller, so the weight can be calculated as 1 divided by the distance. Okay, so in this case, if the distance is close to 0, then you get really high value. If the number is really high, then you get small numbers close to 0. Okay, and you also want to have the total weight starting from 0, and in the end you want to divide the direction by the total weight, so that the the final amount of the direction distance should be normalized. So not normalized, but regularized. or the size will be not too big or not too small. So to do that, I'm gonna add this weight value to the total weight on each loop, and outside the loop you divide the direction with the total weight. Okay, and that should create the final direction for each voxel. Now let's test this. Let's test this out. Let's check this. I am going to update the velocity value of this voxel volume with this direction. And let's change this to vector field. Okay, so let's check how it looks like. I'm gonna check it by using volume trail. So in order to use a volume trail, you need to connect the volume to the second input, and on the first input you place a bunch of points which should be inside the volume. So I'm going to use a scatter node to have a bunch of points inside a volume, then check the direction. Now if you look at the direction, looks pretty correct. I mean, it's being affected by two curves, and the direction does look pretty normal. I mean, natural, I think. Now you could also modify these, how much the distance could affect the flow, by changing this d value a little bit. For example, you can use a power function with some parameters to control how much it affects, how much the distance could affect the weight. Let's change this d value minimum and maximum range from 0 to 3. See what happens. So if I change this, you can see this value changes how the distance could affect, being affected by the distance with the distance to the curve will affect how much it's being affected by those curve direction. Okay, so maybe you could keep it 1 as an starting point, but later maybe we can try changing this to something else to see this difference. But if you make it too high or too low, then you're going to have some funny effect. But sometimes maybe this could also be interesting to test for visual. I mean, since this is not really physically correct, accurate, simulations could be anything. So trying out with these values might be interesting. Let's see. For now, I'm gonna go with 1 for now. Okay. So far I have a basic base vector field coming from the original the base curve that I have set manually. Now next thing I would like to do is to create some obstacle on inside these volume, so that this obstacle could also affect how the vector field be modified or vector field be made. So what I want to have is, if I have an obstacle, or if I have a rock, something placed inside the volume, I want to have the vector field to duck these rock, go around the rock, so that the animation could be, the fluid can go round the rock to flow. Okay, so that's what I would like to have as a vector field, and you could actually do that using some simple vector mathematics or vector calculations. So let's try to do that. So in order to do that, you kind of need to have an obstacle geometry. So obviously, so let's try creating that for one first. I mean, it could be anything. You could just place like a big head here to use it as an obstacle, or if you prefer placing rocks, then you can have multiple number of rock-like shape here. So I'm gonna do something like that. I'm gonna start by creating a sphere. I'm gonna make it really simple, and gonna use a polygon. Okay, I can use something like mountain node to make it look like a rock. Doesn't have to be too precise, but it's up to you. I mean, how much you want to make it as a rock. Just go like this. Okay. Well, anyway, just want to use it as an obstacle, so anything is fine. Okay, now let's also define how many rocks you want inside this plane or volume. So I'm gonna have another scatter node. Let's place something like 10 or 11 rocks, and probably I want to also change the rotation and the scale of the rocks for each rocks on each points. So I'm going to set a P scale and the normal direction so that I have some randomness to those rocks, to those obstacles. So first, let's set the scale. Could be random, so rand based on the point position plus some seed, which then you could change it by yourself later with the parameter. Then let's subtract it by 0.5 for each coordinate. As a result, you get from negative 0.5 to positive 0.5 for each x, y, and z. Okay. Why do I need to set vector value? Okay, I think for a p scale you can just go with this. So from 0 to 1. Maybe if it becomes 0, it's gonna be too small, so let's limit the size, limit the scale size to 0.5 to 1.0. Okay, so that's for the p scale, and let's also set the normal direction using random, using another at p plus seed, maybe adding some additional custom seed value. Then if you're making the vector value, then you might want to subtract it by 0.5 in this case, so that as a vector value you get from negative 0.5 to positive 0.5 for each x, y, and z. Okay, now let's use this to place the rock using copy to points. And see what happens. So now you have a bunch of rock-like shape placed inside a volume like this. Okay, maybe I can increase the base size a little bit, like that. Maybe that's too big. I don't know. Okay, well, let's go with this. Okay, so what I want to do now is to use these rocks to modify the vector field that I have right here. So based on the rock positions, I want to kind of duck or change the direction of the vector field somewhere around the obstacle geometry so that it go around the rock. Okay, so in this case, the information you need is the distance to the rock to each voxels, and you also need the normal direction of the rock so that you know in which direction the voxel, the base vector field that I have right now to be directed to be modified. Okay. So yeah, that's what I would need. And let's think, what kind of calculations would I need to do? Okay, so let's see if I have a direction like this. And if you have a rock like that, the final result that I want to have is something like this. Right? So to do that, somehow you need to modify this vector field and each voxel point by using the information coming from this rock. Okay, so several things you might need to know. One is the distance from each voxel point to the rock, like you did last time. And you also need to know the normal direction on that projected point. Okay. And using those informations, you could calculate a, let's see, probably a dot product from, let's see, using the dot product between the current vector value on a voxel, which in this case this direction, and a dot product of the normal, the point being projected to here, and the normal direction of the obstacle is right here. So you can calculate the dot product between this curve and this vector value. Okay. As a result, you get a kind of projected distance, projected lengths of those two curves, of those two vectors. In this case, you get a positive, some kind of value here. Or let's call this A. Right? If you are looking at this point here, the normal direction is going this way, and the vector field is going this way, then the the dot product is going to be negative value. Right? So based on this sign, you could define whether the vector will be rotated or changed either this way or this way, inward, outward. Okay, and also using the distance to see how much it affects. Okay, so what I could think by using these values is to, let me redraw it. So I have this. So if I have a curve, the base vector field like this, and at some point, let's pick this point, project it on the obstacle, you get the normal directions going this way, and the vector field direction is this way. You have this direction, then you get the dot product between those two. Let's call this A. In this case, this could be negative. Now next, I am going to use this A value to multiply by a distance-based weight. So this is the distance, and just like this original vector field calculations, if the distance is smaller, then you have more affection. If the distance is further, if distance is larger, then you have less affection by the obstacle. So the weight value could be 1 divided by some distance. Okay, and you want to multiply this weight by A and use this together with a normal distance of the obstacle, in this case this direction. So let's call this n, and if you multiply this by n, or n by multiply by these weight value, you can kind of calculate how much you want to move to this direction based on the distance and the dot product. And finally, you can add this normal direction to the current vector value, in this case here. So by adding this vector field to this normal, you can have a vector, the final vector field final vector something goes this direction. If you look at this point, the normal direction is somewhere around here, the base direction is here, and calculating the dot product, let's call that A multiplied by weight, and added by and normal distance, and multiply by normal direction. You are adding these vector by this vector, and probably the direction is going to go this way, which might not be a good direction because it's going, things like it's going this way, but what you want to get is going this way. Okay, so in this case you might want to make this negative. Okay, so and you only want to make this negative if the A is positive. So and in this case you want to make the dot product to be you want to make this to be n, multiply by a, multiply by w, and you want to make this as positive value. But in this case, you want to make it as negative value. So you can use the sign of the dot product itself to use for the sign here. So if you just multiply -1 to a, then you can make these positive, then make this one negative. Since this is the case where a is positive, and this is the case where a is negative, and if you multiply by -1, this becomes positive, this becomes negative. Then you get this kind of a flow as a final result. Not simple, but that's my logic, and let's try that out. So yeah, I admit this is not really simple, but yeah, it took me a little bit of time to figure that out. I'm just telling you the result that I got, so you might not really get it, but you'll see what happened. So first I'm going to calculate the normal direction of each obstacle point using normal direction, and I am just going to, where shall I do that? Well, I can recalculate the velocity within one volume wrangle, but it might be better using another wrangle to modify it, since you can see the flow a little bit better. So I am going to create another volume wrangle. In this case, I'm going to use obstacle to modify the flow. And for the second input, I'm going to connect these rocks with the normal direction. Okay. Now, just like I did previously, for each voxel, checking the distance to each curve, I'm going to check the distance for each voxel to each of the rocks. Okay, so going to do the loop again. I mean, if you want to make a quickest estimation, then you can just get the closest distance out of all the geometries, but there is some possibilities that you're going to have multiple, you might want to change the direction of the flow based on multiple number of rocks based on the distance. So I'm gonna write in this way. If you just care about the closest rock, then it's gonna be more simple, but it's gonna be a bit weird if you have multiple number of rocks which is placed nearby. So let's go with the harder way first. Sound is low, can you hear it? I can't really track the sound much. How is it? Let me know if the sound is okay. Okay, so I'm looping all the rock. Okay, and just like I did previously, I'm going to calculate the distance and the, in this case, not the tangent vector, but the normal distance, normal direction. So primitive UV and calculate the distance using XYZ dist. same thing. Pick the rock number or primitive number. Then wait a minute. Now that I think, it's not really checking per rock, but it's checking per triangles, which is gonna be a bit too slow. Probably I just wanna check per rock to make it a bit more faster, I think. So let's do that way, shall we? So in order to do that, I need to know how many rocks are there. You can get it here. So total, in this case, total 11. So probably I could also have this connected to the third input here and using the third input for a loop. Yeah. Also, I want to add a ID to each of the primitive. So let's, inside this rock volume, let's define an ID value, like index value coming from the point number. Okay, so as a result, for each point you get this index value coming from this original point. Yeah, in total you have from 0 to 10. Okay, now you could go back to the obstacle flow. So you are looping the third input, which in this case you have 11 points, so you have to use n points here. And for each loop you're going to search for the smallest distance to the primitive coming from the second input, which are these rocks. And to do that, you are using a input 1, and the filter is going to be at index equal to I. Okay. Then use at p the point position and prim uv. Okay, this should be faster. All right. Now that you have a smallest distance, the closest distance, you could also get a normal direction using prim uv from the second input. And output the prim using the prim and uv to get the specific position. Okay, now now that you have normal direction, normal direction and the distance, let's first calculate the weight based on the distance. So just like we did previously, the weight can be calculated by 1 divided by d, probably a power of d. Okay, let's also set the range of this power from 0 to 3, just like we did last time. Okay, and let's go with 1 for now. And next I am going to create the total weight here. Add weight to this total weight, increment the total weight by this weight on each loop. Okay, now you also want to have the final vector value. which is the one that I have wrote here. So that's going to be a normal direction multiplied by the dot product multiplied by the weight. So we need to next we need to calculate the dot product between the normal and the current velocity of the volume. So easy to calculate. The dot product is between the normal and the velocity. Okay, that should be it. Now finally you could calculate the temporal direction by multiplying the normal multiplied by weight multiplied by a dot product, and like I explained last time, you're going to multiply by -1 as well. Okay, what else? And that's probably it, I think. I don't know. Maybe not, but let's try with these. And you want to add this to the direction. And finally, outside the loop, you're going to divide it by the total weight. Let's see what happens. And now the final, this is going to be the modified direction on each voxel point. So the final direction you want to have is the addition of the current velocity plus the direction that you have just calculated. Hopefully. Now let's see what happens. And you don't see any changes. Okay, so something must be wrong. Sound is too low? Okay. Can you hear? Okay, I'm raising up the sound volume a little bit. How's this? Can you hear it? How's it? Let me know if you can hear it. Okay, I'll wait a little bit. Meanwhile, still low. Are you sure? How's everybody else? If I'm making too high, the sounds might gonna break, so gotta have to be careful. How's this? Maybe if I make the microphone close to me, close to my mouse. Okay, so where was I? Okay, let me so this one is not working right now, so let's check what was wrong. Okay, so first of all, I have to make sure if this calculation is working correctly. So first of all, I am checking the number of points coming from the third input. Yep. And that has to be here, right? Now let's also check if I have an index. Yeah, there you go. Although I realized that this filter has to be placed on the primitive, not to the point. So I'm gonna promote the index attribute to the primitive. Maybe I can do that here. To the primitive, copying the index. Let's see what happens. So we'll look at the primitive. Okay, it's not being copied, so maybe I should do the attribute promote. So I'm going to copy the index attribute currently inside the point to the primitive. Let's not delete the original. Let's check. So now I have index value applied to the primitive attribute, then the filter should work now. Okay, something happened to the volume, and if I look at the final result, okay, things start to happen, what I'm looking for. And if you overlay the rock, you do see some rotation or some round movement start to happen. Okay, that's good. I think that's good. Alright, so let's see if let's see what happens if I change this power function. So based on the power function, you can see how the distance could affect this roundiness of this flow. So it looks promising, I think. I don't know. If you have more of a Goch-like style, you could go somewhere like this. If you make it 10, it looks more like a Zen garden, but looks more like, if you're looking for more natural flow, maybe 1 to 2 may be good. Okay, so seems it's working. So next thing I would like to do is to use the vector field that I've just created to actually animate some flow, animate some particles based on using these vector field. Now that part is not that important, but let's just do it as a fun. So this is the final result that I got as a vector field. We can now use this together with some, I don't know, Subsolver to animate particles. So Subsolver, just solver. Okay, and let's see how fast is it by changing the rock position and stuff. I'm going to create the null node so that I can have multiple, I could have parameters that I want to change later, something like random seed and stuff. Okay, let's see what kind of parameters that I want to change. For example, the basic size for the rock. The number of rocks. In this case, random seed. What else? So these are for the rocks, which is not that important. Okay, next we could have a size of the original grid, probably. plane size. We could maybe later try with some 3D surface or 3D geometry. Maybe if we could make a flow on top of like any kind of 3D surface, that might also be interesting. So maybe we could try that later. But for now, let's go with the plane. Then there's some resolution for the volume. And the curve I'm just gonna leave it here so that you can change it manually by yourself without using those values. And the power value for the flow, the velocity, power, and curve power. And you have an obstacle power based on the distance. Okay, what else? So you have this is just to check, so it's not really important here. Okay, this is the final vector field that you have, and let's see how this final vector field changes by changing the parameters. Okay, so okay, it's fast enough, I think. Changing the total, oops, the total number of rocks has to be limited, I guess. I don't know, maybe maximum 100. That still is a lot, but let's say that's maximum. Okay. Yeah, seem to have some effect. Seem to have an effect that I'm looking for. Yeah, looks not that bad, I guess. Okay, by changing the resolutions, you can have more complex control for those volume. Okay, looks good. Curve power. Interesting. Obstacle power. Okay, not bad. Okay, so now that I have these basic control, let's use this to create the actual animation using this vector field. So let's connect the vector field to the second input to the solver, and let's give a initial particle, initial point position to animate to the original grid here. Okay, so where is it? I'm gonna give another scatter node. Let's give, I mean, this could also be parameterized, I guess. I don't really need to relax it. Maybe, yeah. Or maybe not. It's up to you. So let's say this is the initial point for the particle. And for each frame, I want to increase the number of points running through the plane, and you also want to delete the point at some point, because if you keep adding the points, then it's gonna be really slow. You're gonna have too much points inside a plane, so let's give some conditions, like for example giving a life value to each point, and then if the life becomes 0, then those particles disappear, and also if it goes outside the grid, then it might also die as well. So based on those rules, let's try creating and deleting the point. Now for the initial points, I'm going to give the initial life value and each step I want to move those points based on the direction that I have here from this volume, velocity volume. So the life could decrease by 1 in each frame. I'm just gonna give some integer value randomly created, and let's decide the maximum life. I'm not sure what's the good value, so should be parameterized to check what's the best value for this one. I'm gonna stop by setting to 50. So from 0 to 50, you got the life is gonna be from 0 to 50, and based on this life, some points disappear faster, some points lives longer. And you're gonna control this life inside a solver. Okay. Now, so let's try to move this point. Using the volume, the vector field coming from the second input. So for each point, you're gonna sample the volume, the velocity, direction, and based on those direction, you're gonna move the point to that direction. So to do that, you're gonna use a function called volume sample v. Okay, that is coming from the second input. The name of the volume is called velocity, and you're gonna use the current point position as a sampling value, and as a result you get a velocity. And let's just normalize it for a simple calculation, meaning you're gonna make the distance or the length of the direction to 1 to have the constant speed. Now I'm going to multiply this velocity by a actual speed, how much you want to move this point with. It depends on the size of the original grid, so if it's like 10 by 10, then maybe for each frame moving by, I don't know, 0.1 might be good enough. Okay, then finally update the point position by this velocity vector value. Okay, let's see what happens. So currently I'm not adding new points, so what's gonna happen is just moving these existing points to with the vector field. Okay, so yeah, it looks like the point is moving, that's fine. But as you can see, at some point the points just stops. And that happens when it goes outside the vector field or inside or close to the rock, or where the vector field stops or blocked by other vector field, other vectors. So in those cases, when the point stops or when it goes outside the plane, you might want to delete it and recreate the new one, or keep adding the new one on each frame. But first of all, let's create some conditions when to delete, or when to move the point. Now for the point which goes outside the boundary, maybe it can go reappeared from the other side. So if the point goes to the right side of the plane, then it might be able to come back from the left side of the plane. Same for the top and bottom. So let's create some conditions for that. First, I'm going to get the boundary of the plane by checking. Maybe I can just use this volume as a base geometry to check the boundary. I'm going to use the get bbox to get the minimum and maximum point position of the bounding box. Gonna look at the second input. Now, if the current point position x is more than max x, then the point x could be reappeared from the min x. Okay, and you could also change the z value. I don't know, maybe keep the z value as it is for now. And if the at p dot z is max dot z, then do the same thing. Z is going to be minimum z. Okay, so that's when x goes to the right, coming back from the left, and this is if the z goes to the bottom, come back from the top. Now I want to do the other side as well. If the x goes to the left hand side, the point goes to the left hand side, then come back from the right hand side. So in those cases, you can say else if at p dot x is less than minimum x, then at p dot x could come back from the right hand side, which in this case max dot x. Do the same here. Else if z is less than minimum z, then at pz is equal to max dot z, like that. Okay, let's see what happens. So if I play it, okay, not as I suppose. Okay, well, it seems like it's bouncing, go top and bottom, back and forth. So maybe not as I expected, but that is because of the flow that I have here. So yeah, not much I can do for these. So let's say I'm okay with that. Okay, so for now that's okay, but obviously I have too small number of points to make it look like a flow, make it look like a fluid. So let's create a bunch of points on each frame as well. To do that, I am going to incrementally add additional points, probably using the same setup that I have here as initial points. I'm going to copy this, paste it here, and Scatter points. Okay, in order to scatter points, I might need additional geometry. Rather than using the velocity volume to scatter, probably need original plane connected to the third input. Like that. Just like I am creating the points from the plane, I want to do the same here. And for each frame, I want to add new points using this scatter node, but to the different positions. Right now, even if I change the frame, the point position doesn't change, so I need to set a frame to the global seed so that each frame you get different point position being created. Then I can apply the life to this point randomly. Let's check the life attribute. Yep. And now I could merge this point to the previous frame. Now I also have to make sure that the point is going to be deleted when the life becomes 0, and you also have to make the life goes down by 1 at each frame. So let's do that somewhere. Where should I do that? Maybe I can do that on the move node. In the last, you could decrease the life by 1, just like this, and then check if the life is 0 or not. Deleting the point, or you can just use the delete node, I guess. Life. If the life is less than 0, then just delete it. Less or equal to 0. Okay, and let's see what happens. Okay, so you start to see those flows with those points. And let's also check the total number of points that I get with these simulations. So 2,322 or something. Let me copy this life parameter being linked to this max life, as well as a number of initial points created on each frame be copied here. Now if I increase those two values, obviously the total number of points that I get is gonna increase a lot more. So let's see what happens if I increase these to 300 points with 100 life. So at some point you might going to have too much points. So it might be better to have a limit, the max point like number as a parameter, as an additional parameter. So that if I want to limit the total number of points to 10,000, then I should limit. I should have it as those I should have it as a parameter. Now I also see those points which are not moving, so maybe I want to also do something about those as well, like those points. And that is probably due to some vector value that I have here, somewhere around here, which is causing these points to stop somehow. Not sure why. Let's see. It's stopping somewhere around here. And I realized that it's going on 3 dimension, and then I think that's why. Okay, so I gotta have to make sure that the point only moves on those on top of this plane. Okay, so in order to do that, the initial point is on top of the plane for sure. The problem is probably since this normal is 3-dimensional, I mean it's not really related, it's not really always flat. So because of this, the actual vector field that I got here is not really projected on the surface, but it's more 3-dimensional. So things you could do is to project the vector field that I have here to the surface, to the surface that I have here, which is and later I might want to make this as a 3D surface, so I don't want to just project it on XZ plane, but I want to project to this specific plane. Okay, so to do that, I first going to, and because of that, it might make sense to have a bunch of grids here and calculate the normal for this grid. Okay, and in order to project this vector field to this normal, I could do this right here, or I could have another volume wrangle to do that. I mean, I think it's always better to do it in one node for efficiency, but just to, in order to see what's happening, might be better to split the functions in different node. It's up to you. If you're looking for the speed, then writing on one node might make sense more. But in this case, this is more like a educational purpose, so let's separate the node. Now connect the node surface to the second input, and now I want to project the velocity on top of the surface. So to do that, you kind of need to know the X and Y direction for each voxel projected on the surface, and use those X and Y direction to actually calculate the projected direction. Now what I mean is, for example, if I have a vector field like that and I want to project it on a plane, somehow I need to get this. And in order to get this, what you could do is to first of all have a normal direction, okay, of the projected point, or projected point for the starting point of this vector value on a surface, on a plane. You could get this normal direction. Now, next thing you want to get is some axis value on a plane, such as x-axis and perpendicular y-axis. Okay, and combining these two axis direction, you could recreate this projected vector value. In order to do that, you could calculate the dot product between the x and this direction and the dot product between y and this direction. And the result is the projecting this vector to x, getting some kind of distance for x direction, and projecting this to the y, getting some y axis direction amount, a distance. So multiplying x direction by dx plus y direction multiplied by dy will give you this final projected vector value. If this dy is negative, then the y's direction is going to be in this opposite direction. So, and this x and y could be anything if it's perpendicular to each other. So if it's perpendicular to the normal as well. So that's the only information you need. So what I could do, first get the normal direction for the surface by projecting this point to the surface. So again, you could use something like xyz distance to get the primitive and uv. In this case, you don't really need the distance, but you need this primitive and uv in order to get the closest normal direction. So by having primitive and uv, you can get the normal at the projected point position using prim uv. Okay, now from this normal you could get the x and y. So in order to get that, could be anything. So you could start by creating a random vector value. Let's call this random vec. Based on the current point position. And by calculating the cross product between the normal and this random vector value, you can get the perpendicular vector, the vector that is perpendicular to this normal. And let's normalize this so that the length will be equal to 1. Then I could actually call this as x-axis vector value. Now the y-axis can actually be calculated by calculating the cross product between the normal and this x-axis. Also normalizing it. Right. So now I have x and y and should be perpendicular to each other. Normal x and y. So this could also be called as z-axis. Okay, and having those two axes which should be aligned with this surface, you could project the current velocity on top of the surface by calculating the dot x, which is between the dot product x-axis and the velocity, calculating the dot product for the y-axis by y-axis and velocity. And finally, you can calculate the projected direction to the surface by multiplying x-axis by dot x plus and y-axis multiplied by dot y. And let's check the result. Update the final velocity with this projected direction. And if you look at the result, the vector should be flatly aligned. And now I should see all the points being moving without stopping at some point anymore. Okay, let's check. There you go. Better. All right. So where was I? I wanted to limit the total number of points. Currently I have like this much number, but if I want to limit the number of points to like 10,000, then I should have that kind of parameter probably assigned here. So let's have that together with all the parameters that I already created. First, I am going to define the max particle number. Okay, and let's say the maximum is 10,000. Copy it. And in order to limit the number, I want to delete the older particle, the particle with small life first. So let's sort the point based on the life. Okay, and reverse it. So that, or maybe not reverse it. Which one should I keep? Yeah, let's reverse it so that the points will be ordered from the higher life to smaller life. And from 0 to 10,000 is the one that I want to keep, and all the rest with small number of life should be deleted with the limitation that I'm gonna create now. So I'm gonna create another delete here, and the filter should be from 0 to this max particle number here, which I could copy it right here, paste it here, and delete non-selected for the point. That should limit the point number to 10,000 plus 1. If I want to make sure that it's 10,000, then probably I should subtract it by 1 here. Nah, didn't work. I should do this here. There you go. Okay. So now I think I should be able to limit the total number of points, even though if I have a higher life value or high emitter value. Okay, now let's have all the parameters applied to the controller. For example, the number of particles being emitted on each frame. How do I call this? Emit particle emit num. The maximum, I don't know, maybe 10,000. I mean 1,000 is enough. And you have max life for the particle. Okay. And what else? This is okay. Let's go inside. So you have a speed. How fast you want to move the speed. What else? These are just being okay, that's probably it. And you might also want to make these point as a line so that you know in which direction the point is going or directing. So let's give additional attribute to those points by copying this current velocity to this attribute, to this point attribute. And I am just going to call velocity, update velocity with the current velocity that I have right now. Right. Without, maybe with the speed is fine. I don't know, maybe without the speed, just to show the direction. So to normalize it. Okay. I don't know, it's up to you how you want to visualize it. Then finally you could, if you want to show the line as a direction, then you could, maybe I could instead use normal, which will give you an instance visualization in which direction the point is moving to. And you could also use this normal direction together with the copy to SOP. Together with the, I don't know, such as line. Okay. Should be here. Okay, and this should be directing to Z direction, is it? Yep. The scale should be smaller. There you go. Okay, starting to look like it. All right. And if I merge it with the original, I don't know, rock geometry in this case, which is supposed to change the direction, looks pretty promising. And if I change the side of the rock, gonna reset the solver, it does seem to affect how the vector field's being created with decent speed. Yeah. Okay, well, there are other stuff that I could try, but let me check the comment at this point. If you animate the seed of scatter, not inside, and just merge the input one to previous frame, it also work. Ah, okay. Yeah, that should also work. Yes. Yep, so as Aquib was saying, that also works. Okay, so the other stuff that I want to try to implement is some wavy surface. I'm gonna show you the one that I had initially. This is the original geometry, and as you can see, there are some wavy surface here. Okay, and I'm using this wavy surface to project these flow on top of it, so that it gonna look a little bit more organic in terms of the flow, more like an ocean. Well, it's really fake. Everything is really fake, but just to make the things a bit prettier. Let's also try that as well. Okay, so let me just organize this a little bit. So this is the rock. This is where you are copying the rock to. This base field. Then you are having the vector field. And this is the particle. Okay, and this is the solver. Okay, now as an addition, I want to create some wavy surface coming by modifying this original grid a little bit, which is not that important, but might be fun to do. Okay, so let's do that by animating this grid as a, I don't know, ocean-like surface by either using mountain node or using vex. Either way is fine. Thing is, if you use mountain node, it's gonna be a bit slow, I think. Let's see. I'm gonna subdivide it. Make bunch of points like that. If I use mountain node, something like Wally Cellular, you could create an ocean-like wave pretty easily. Pretty fakey, but let's make it a bit more high res like that. And then if you want to animate this, you could move something like this one offset, or anything else. Animation, animate noise. It's not doing anything. Oh yeah, this one is So if I play it, okay, maybe this is fast enough. Maybe that's good enough. So I'll just go with this. Let me know if you're interested in how you could do a similar thing in Vex. Then I could show you, but if not, I'll just use this. Now, just want to use this to project the final output. So what I'm gonna do now, I'm gonna project. Let me calculate the normal of the surface. Project it using something like ray or and want to make sure it's being projected on, I don't know, y direction. So let's make this vector value, oops, delete 0, 1, 0, or maybe -1, and I want to make sure that this surface is lower than the original plane. Okay, so let's translate this a little bit lower to the negative y direction so that you always get some intersection. Okay, there you go. Now you're running the flow on top of the surface like this. As a result, you get a bit more interesting flow like that. Now you might also need to move these rocks together with this movement, but I realized it might not work if I use the 3D surface as a goal, so maybe I'm gonna have to rethink using this. Maybe it's not really appropriate to use a constant value like this one after all. So let me rethink that. Probably I should use the direction that I have retrieving from the surface, the original surface, and this will give you the normal direction in which direction it should be projected. So let's use that. For the final output, I'm going to refer to the original geometry with the normal. And as always, I'm gonna calculate the XYZ distance. Get primitive and UV. And what you want to get is the normal direction. And using this normal direction, you want to project it to the surface, like here. Okay, so let's do that. I could if I'm using the ray node, then I could use this attribute, but I also have to make sure that the surface is either inward or outward of the original surface, so that's a bit tricky here. Yeah. That's a little bit tricky here. Let's see how I should do that. Now, if I gonna use vex, then I could just use intersect. Maybe I could do that. So I have the normal, I have the original point positions, and if I want to calculate the intersect to this surface, then I could do that by intersect to the third input. And what was the parameter? The original point position could be at P plus normal multiplied by, I don't know, 10, some big number. Then the direction could be negative normal multiplied by some higher number. Then as an output you get the intersected position and UV. Let's just create the empty variable. Okay, and the actual information that I need is this intersected position, so I'm going to move the point to this intersected position. There you go. Let's see. Okay, I think it's working. Now, if you merge these surfaces together, you could see that the vector which has been projected on the surface is not being aligned with this wavy surface. So if I want to align that as well, you need to calculate this normal direction, the current normal direction, which defines this direction with the normal getting from the wavy surface. So to do that, the final direction could be a cross product between the current normal to the wavy surface normal. Then you can recalculate the cross product between the one you get here with which is perpendicular to oops, the result you're getting here is the perpendicular vector value, which is between this one and the normal surface, the normal of this surface, which is somewhere around here. And having this, by recalculating the cross product between this perpendicular product, perpendicular direction with the normal of this wavy surface, you get the final projected direction. So like that. And let's normalize this. See what happens. Updating the normal with the direction. Might be in the opposite direction, so let's check. It doesn't seem correct. So something might be wrong. So I am using this one. If I place it right here, oops. Okay, it's not really correct, so maybe I'm getting wrong information here. The norm, oh yeah, this is wrong. This is not the actual wavy normal, actually. I have to get it from here. I have to re-get the normal direction from here. this UV with this enter information. So the wavy normal is prim UV, third input, normal, enter UV. This should be it. And I have to replace this here, here. There you go. Now the curve has been projected to the wavy surface. And the animation should be more natural now. Let's check. Yeah, I don't know what's the purpose of using this, but just for fun. And let's, since this is on the exact same position to the surface, let's offset this a little bit to the wavy normal direction, or to the, I don't know, plain normal direction, by adding a little bit of offset value. Spell mistake. Okay. Here you go. Not bad. Alright. Okay, now I want to try by changing this plane to a 3D surface to see if this could still work. I might need to change something, but right now it works for plane, but I want to make it work for 3D more curvy surface as well. Even though that's not a natural situations for ocean, but why not? Since everything is fake. Okay. So I want to make an option. I want to make an option to switch between different geometry. For example, I don't know, pig head. Which could be a harder situations to see. Now let's make this big enough. Okay, currently subdivisions is a bit too high. So let's make this as the parameters. I think this is high enough. Okay, let's have a wavy surface based parameter. Just this. Subdivision. Subdivision number, as well as, I don't know, mountain height. As well as element size, which will enable you to change the size of the wave. Okay, that's about it. Now, let's see what I need to change here. So I have a bunch of rocks. The first thing I need to make sure is the vector fields being created correctly or not. So let's see. This is where I'm checking the vector field. Okay, Not really sure if it is correct or not. Let's see. Together with the rock. Okay. The vector field is somehow trying to avoid going through the rock as much as possible. Let me see. If this vector field itself using this curve, is this really be affected by this original curve? Not sure. So let's uncheck this and also uncheck this as well. Okay, so this seems correct. So the base curve orientation looks correct if I try to move the curve. Yeah, seems it's been affected, so that's good. Now next, looking at the obstacles. Might want to increase the number of points to check. Let's make it 10,000. That's a little bit bigger. Let's decrease the trail size. But now I could see the rock is affecting the flow. Let me try changing the power. Yep. So it is still working on 3D vector field. That's good. Now the last one, this is projecting the curve onto the surface so that the the flow is aligning on top of the surface, and that is also seems to work. Yeah, probably, not sure. Okay, let's see if it is, and let's check how the particle is running. Somewhere around here. Okay, save it, play it. Okay, I am seeing some flow here, and okay, something is happening here. Doesn't seem correct, so let's check here. This is where I'm creating a wavy surface. Ooh, interesting. Okay, now this is where I'm projecting the point to the surface, and this is where I'm getting some unexpected result. Thing is, some points are not getting an intersected point position, so that is the reason. So I gotta make sure if I wanna only move the point if the intersect has been found, meaning if the inter is larger or is equal to 0, then that means you have found the intersection. That's when you want to move the point to the surface. Yeah, that'll do. Okay, and moving the door, adding all these informations together. Okay, well, doesn't really look nice. Not sure what's happening here. The way the line moves doesn't look correct, is it? Some points. Well, I could imagine the vector fields being stuck in these kind of positions. Maybe the speed is a bit too high. So let's reduce the speed a little bit. Oh, interesting. Maybe that's too slow, but overall it's moving in the right direction. So I guess this is also okay. But obviously this is too slow. Maybe for this kind of 3D surface, I might need to increase the maximum number of points. I don't know, to 100,000. In this case, I could also increase the particle emitting number as well as life. And I could probably also increase the offset, or maybe it doesn't really affect much. Oh well, I guess it's working. I mean, don't ask me what's this for. It's just for fun. Okay, but at least it's using an obstacle to move around. Seems it's working. Alright, let's try with the simpler geometry like sphere. See what happens. Something like that. Reconnect to reset the solver. Maybe I need to change the obstacle power a little bit. Since it looks like it's going through the rock here somehow. That is probably because interesting. What's happening here? Let's see what's happening here by just looking at. So it's rotating like this. So maybe it's not really going through, but it's having a self rotation, or yeah, a tornado or turbulence somewhere around here. Interesting. Well, this is just simple vector calculations like we see, so it's not really perfect. But at least it has some effect. So, hope you like it. And yeah, now by using this, you can change how you could change the face wavy amount. Alright, not bad. I think overall, I think I really like the result. So let's make additional parameters like changing the shape. Let's call this shape as an integer value to switch between the base geometry. Let's also make it a bit prettier by setting some colors to the surface, the wavy surface that I have here. I am going to color it based on the height of the surface. Let's make the subdivision maximum number to 4. And I'm gonna set a attribute to each point based on the height of the surface. Or well, I gotta also think about the original surface. If it's the 3D surface, then you cannot just take like y direction, but instead gonna have to get some other information. Now it might just make sense referring to the original surface like this one and compare the current point position, just compare the distance between the original surface and the current point position. Yeah, that might make sense. And also you can also get the signage if it's on the upper position or bottom position to the original surface by calculating the dot product. Yeah. So the original position is 0.1 at pt_num, and the distance is distance between the original position and the current point position, and you can assume whether it's upward or downward by calculating the dot product between the current point position minus O position and the normal of the original surface, or the current wavy surface. Either way is fine. I'll just use maybe I want to use the original normal direction. Do I have that? Yeah. So, oh, it's been deleted. Original position, getting from the second input at pt_num. You can also get the original normal at pt_num. The distance is distance between the original position to the current point position, and you can calculate the dot product between the at p minus O position and the original normal direction, and you can multiply you can, let's say, create the color attribute which can be a multiplication of distance by a sign of dot. Alright. Forget to write dot. Okay, now you can use this color attribute to actually color from minimum distance from the bottom to top. Now you also need to retrieve the maximum and minimum of this color attribute, so attribute promote. Point to detail, color, minimum, min col. Do the same for the maximum. Maximum. Finally, use color node to color the attributes. Let me check if I'm getting the right value. So I have color and I have the minimum and negative here. Okay, minimum, maximum, and using the color attribute, and the minimum is detail OP input. The name is min col 0. Okay, and the maximum is max col detail. Okay, now you could just change this to any color you want. If you want to make it look like an ocean, then make this black, having a little bit of blue here. Alright. Okay. And let's check by changing the surface. For example, if I change this to pig head, it's a bit hard to see because I also have textures. Let's go with the sphere. Okay, not bad. Okay. Okay, I think it's good enough. All right. So I think that's pretty much it. Let me know if you have any more questions. Or feedback or anything. This logic could work very well for real-time liquid sim. Probably, yeah, you could implement the similar things with shaders, I think. So since everything is being written in Vex, it's pretty easy to implement it in shader, I guess. Not easy, but possible. So I think that's pretty much it that I wanted to show today for today. Hopefully you liked it. Oops. Let me know if you have anything to say. If not, I'm going to end the live for today. Let me also bring the color attribute, color parameter here. color. Okay, do you have any plans to make a video on point relaxing algorithm? I think I have done a point relaxing a while ago. For example, like sphere packing or point circle packing, or Lloyd algorithm, or something like that. But if I found any other algorithm that I didn't try, then yeah, definitely I would like to try. If you know any good algorithm to try out, let me know. Probably in the comment. Okay, so probably that's pretty much it. Thanks for joining today. Thank you for all the comments and feedbacks. Reason why I'm asking is because I wanted to explore how collision work in Houdini. Oh, one of the way you could use is again some dot product or a distance based forces, more like a spring based forces. I think there are many ways to implement that. So I mean, I did a bunch of those stuff in past videos, so if I found something that I didn't try, yeah, I will definitely try. Will you make a geometry node? What? I didn't get it. Geometry node? You mean this one? This is a geometry node, isn't it? Sorry, I didn't get it. Well, as always, I am going to I'm going to save the file, share the file to you. I'm going to paste the link to this file to the description page of this YouTube live stream, so that you can try it by yourself. And what else? The video is going to also be archived, so you can watch it later if you're interested. Okay, and just to mention, I'm also having my own Patreon page, so if you would like to support me, that would also be great. If you like to, if you're willing to, that would be great. But everything, basically I'm just sharing everything free, so because I don't know, knowledge should be free, so it's my philosophy. So just in case, if you like to support me, that would be great. I see Blender geometry node. Yeah, I did try using geometry node like a year ago probably, and I did enjoy that. And I noticed that the recent geometry node has a bunch of interesting node like solvers and stuff, so yeah, I would love to try that again. Since Blender has better real-time renderers. Eevee, that was it. Yeah, I like that one. So for sure I would like to try that out. VDVs are now importable in Unreal, so maybe some implementation. That will be really interesting. Yeah, definitely would like to try that. I didn't know BDVR possible to import. Like fogs, you could do that. Interesting. That will be really great. Okay, so I guess that's it for today. I've recently tried using UEFN, which was a bit limited in terms of the editor, but also fun. So maybe if I could make some simple video about it, that might also be fun. Okay, thank you for joining. That's it for today. Well, good night and see you next week. Next week, I'm planning to implement a lenticular effect, a physics-based lenticular effect, which is not that hard to do, but interesting to see in computer graphics. So if you're interested, please join. Okay, so good night and see you.